uniform circular motion. Circular, as the name suggests, means the trajectory is a circle. Uniform means the speed is constant. And motion, of course, means the object is moving with respect to an observer at rest, someone watching the motion from outside. So the trajectory is a circle. This is the path followed by the particle. The particle has mass m, and it is moving on this circle with a constant speed. For linear motion, we had position x, velocity v, and acceleration a. We need something similar for circular motion. When it comes to circular motion, we are not referring to the displacement x anymore. We are instead referring to the angle swept by the particle in a certain amount of time. So let's say the particle was here at time is equal to 0, and it will be later here at time is equal to t. During this time, the particle has done two things. Has traveled distance s and has swept the angle theta. If we label the radius of the circle r, which is going to be constant, it is a circular motion, we can relate these three quantities as s is equal to r multiplied by theta, but the angle theta must be in radians. If it looks complicated, just think what happens during one full circle. During one full circle, the particle has swept an angle 2 pi radians. It is our 360 degrees, but we are not working in degrees. What is the distance traveled by the particle as it completes one full circle? R multiplied by the angle theta, which is in this case is 2 pi. So the distance traveled by the particle is 2 pi r, which is precisely the circumference of a circle, an expression that we have seen before. Well, the particle is moving. So although the speed is constant, the velocity is not. The particle is moving on a circle. Here, the velocity is like, let's say it looks like this, while here, it looks like this. So, although the speed has not changed, the direction of these vectors has changed. These two vectors are not equal. Their magnitudes, their magnitudes are, but their directions are not. Two vectors are equal only if their magnitudes and their directions are the same. So, because of that, we will have an acceleration. Because acceleration is not the change in speed over time, it is the change in velocity over time. That we have cases in which we can use these two words interchangeably, that is a different story. But not in this case. Now let's clarify something you're probably already thinking about. Why is the velocity tangent to the circle? Why is the vector velocity v like this? Let's pretend we zoom in as much as we can here. And what do we see? We see the object traveling in a straight line. If I zoom in here, this is what I see. It is a straight line. It is not a circle. It is not a curved path anymore. So, in a tiny amount of time, I see the object traveling this tiny distance, which of course leads to the velocity being in this direction. We already saw that the relationship between s, theta, and r is given by this. But as I mentioned before, I can look at the motion from two different perspectives. One is in terms of the distance traveled in meters, and one is in terms of the angle swept in radius. Well, let me divide this by time. I will get a distance traveled over time. The radius has not changed. And I have an angle swept over time. This is precisely the speed v. This is a new speed that accounts for the change in the angle during the motion as opposed to the change in distance. So this new quantity, we labeled it as omega. This is the Greek letter omega, and it is the lower case. And this symbol is well established. That means we have a second expression, v is equal to r multiplied by omega. The two expressions, s equals r multiplied by theta, and v is equal to r multiplied by omega, are obviously related to each other. We obtain the second one from the first one simply by dividing by time. And also, what they have in common, they relate physical quantities expressed in meters and meters per second respectively, with the physical quantities expressed in radians and radians per second respectively. Because the unit of the angular speed is the unit of the angle divided by the unit of time, which would be radian divided by second. Now, those of you with a keen eye might notice that something might be wrong with the units. The unit of V must be equal to the unit of R multiplied by the unit of omega. The unit of V is meter per second. The unit of R is meter. The unit of omega is radians per second. And the left-hand side and the right-hand side do not match. What do? I do not do anything. The radian is very strange. It is a unit, but at the same time, it is not. It wouldn't be wrong to say that the unit of omega is 1/2. It would be correct. But to make things a little more clear and for me to follow the formulas a little better, I can write them as radians per second, and they are both correct. It is a strange thing to treat the radian as a unit, but also to keep in mind that somehow it is not a unit. We saw a few minutes ago that although the speed is constant, the velocity is not. And because of that, we have an acceleration. We are not going to prove it in this course. The proof is using geometry exclusively. But this acceleration has the expression v squared divided by r. Or, of course, if we use our newly found relationship between v and omega, this acceleration can be written as r squared omega squared divided by r. One r cancels out. It can be written as omega squared multiplied by r. They are both correct, and they can both be used interchangeably. The direction of this acceleration is always towards the center of the circle. No matter where the object is, this acceleration will be constant, and it will point towards the center of the circle. Constant because v is constant. Remember, the speed is constant, but again, the vector v is not constant, and the radius of the circle is obviously constant, which means the acceleration, which is v squared over r, is constant. But again, the acceleration vector is not constant. Look at the picture. It continuously changes direction. To summarize so far, if an object is moving on a circle, at any given point, the velocity will be tangent to the circle, and the acceleration will be pointing towards the center of the circle. The name of this acceleration is centripetal. Centripetal acceleration. It comes from a Latin word that indicates the fact that it points towards the center. Well, if the object is moving on a circle, we have to define the period. The period is the time it takes to complete one revolution, one complete rotation. That is the definition of the period. And we are using the symbol big T. Little t, we reserve that symbol for time, for any time. Big T, we reserve the symbol for period. So a specific time, the time that it takes the object to complete one revolution. Well, let's find a relationship between the speed and the period. Let's think about it. Time, as we know, is distance divided by speed. If we are talking about one revolution, let's see what happens. The time will be labeled as uppercase T. The distance is the full circle, 2 pi r. And the speed is simply v. This is the simple relationship between the period and the speed. The linear speed, maybe it would be a good time here to emphasize that v will be called from now on linear speed to distinguish it from omega, which is the angular speed. Or we can look at the same expression, time, but instead of distance, we can say the angle swept divided by speed. But now we have to be very careful. It's going to be the angular speed. So again, if we look at this expression just for one revolution, the time again will be big T, the period. The angle swept will be 2 pi. It's 360 degrees, but we don't work in degrees. While the speed will be the angular speed. So we have another expression for the period, this time in terms of angular speed. Are these two equivalent? Let's check. Is 2 pi r over v is equal to 2 pi over omega? Let's check. 2 pi cancels out. R omega is equal to v. And this is something that we saw before. We saw this before. So to summarize, I don't know what happened with my papers. To summarize, what we learned today in terms of circular motion is the following. Circular motion, I can look at it from the perspective of distance traveled, that will be in meters, or angle swept, and that will be in radians. If I look at distance, I'm working with linear speed, v, that is in units of meters per second. Or angular speed, omega, which is in radians per second. Because velocity is not constant, although the speed is, I have an acceleration that I call centripetal acceleration. And this is equal to v squared over r, or omega squared r. Velocity is tangent to the path. Acceleration, the centripetal acceleration, points towards the center. And finally, we have the concept of period, which is the time required for one revolution, which will be either 2 pi r over v, if we look at speed, if we look at distance traveled divided by linear speed, or it will be 2 pi over omega, if I look at the angle swept divided by the angular speed. And one more idea. Period is inversely related to another physical quantity called frequency. So if period is number of revolutions, if period is the total time divided by the number of revolutions, frequency will be the number of revolutions divided by total time. So period, we label it big T. Frequency, we label it f. Let's see. We have an object completing 10 revolutions in 5 seconds. 10 revolutions in 5 seconds. The period will be 5 seconds divided by 10. The period will be 0.5 seconds. Indeed, if it takes 5 seconds to complete 10 revolutions, right? How many seconds will it take to complete 1 revolution? On the other hand, the frequency is the number of revolutions completed in 5 seconds. So this will be 2 inverse second. The inverse second has a name. We can call this 2 hertz. The symbol, the unit frequency, is also called hertz. But a hertz is nothing else than inverse second. So our previous equation that related period to angular speed, t is 2 pi over omega, the angle swept with this speed. If I look at the fact that the period is 1 over frequency, which comes simply for reading this carefully, time divided by the number of revolutions, or number of revolutions divided by time, They're clearly the inverse of each other. If we put everything together, 1 over f is equal to 2 pi over omega, or omega is equal to 2 pi f. This relates the angular speed to the frequency. So for example, if we read somewhere that something is rotating at 20 rpm, this means 20 rotations or revolutions per minute. First of all, I have to understand that R stands for rotation, P stands for per, and M stands for minute. How do I convert this to something that I can use in an equation? Well, 20 stays put. One rotation, however, corresponds to 2 pi radians. Remember the 360 degrees. Per means fraction, and minute means 60 seconds. So that means that 20 rotations per minute corresponds to 4 pi over 6 radians per second, or 2 pi over 3 radians per second. So the RPM is a unit of angular speed. Unfortunately, however, there will be problems and there will be textbooks in which they call this angular frequency. We have to be careful not to put too much emphasis on the word frequency, but to focus instead on the unit. RPM means rotation per minute, which means radian per minute, which becomes second, and radian per second means angular speed.